Hello class, I'm working out of your Algebra 1 book, 7.1 Graphing Systems of Equations. In your first example, you are given two equations, x minus y equals 9, 2x plus y equals 9, and you were also given two ordered pairs, 11, 2, and 6, negative 3. To determine whether each of these ordered pairs is a solution to the system, need to substitute your x and y in for the x and y in the expressions given. So I'm going to say here for x and y, 11 minus 2 equals 9. Yes, 9 equals 9. Check. Now that ordered pair is a solution for that expression, but let's check over here. 2 times 11 plus 2 equals 9 is 22 plus 2 equals 9, and that is not true. So this ordered pair is not a solution, it's false, because it does not fit in this expression for the system. If it doesn't fit in one of the expressions, then it can't be a system on the graph. Alright, 6, negative 3. Everywhere I see an x, I'm going to plug in 6. Everywhere I see y, I'm going to plug in negative 3. So 6 minus a negative 3 for y equals 9. Minus a minus is plus. 6 plus 3 is 9. Check. 2 times 6 plus a negative 3 equals 9. Okay, 12 minus 3 equals 9. 9 equals 9. Yes, true. The ordered pair 6, negative 3 is a solution for the system of equations. Alright, example 2. Solve the system by graphing. We are given y equals a negative x minus 2, and we are given y equals an x minus 4. Okay, so we have the y-intercept or slope-intercept form here, and if that is true, we can determine what our slope is for this equation. It's going to be right here. There's an invisible math rise over run of a negative 1. And when we plug in 0 for x, it's going to leave y equals a negative 2. So our y-intercept is going to equal 0 for x, negative 2 for y. That is a plotted point on the graph. Okay, on this one, we have a positive rise over run and invisible math for our slope. And for our y-intercept, we worked with this in class a lot. We're going to plug in 0 for x, which leaves a y equals negative 4. So 0 for x, negative 4. That's actually a plotted point on the graph. Alright, so you're looking for where these two equations become a system, which is where they cross each other on the graph as a slope line. That point of intersection creates a system, letting these two equations work together. So we're going to transfer our information to the graph. Our first one again is a slope of negative 1 with a y-intercept at 0, negative 2. Okay, I'm going to work it in red. So we have 0, negative 2. I'm going to plot my point. If you remember, we have a negative rise over run of 1. So I'm going to work with a run of 1 and a rise of a negative 1. How'd that happen? Here's a run of 1 and a rise of negative 1. It's going to go opposite. What you think? Your other clue is it's going to be a negative slope on the graph because the slope is negative. Rise of 1, run of 1. To continue the line, rise of 1, run of 1, rise of 1, run of 1, rise of 1, run of 1. This red line, which I should use a ruler, pen, and paper to do this, is the y equals negative x minus 2 line in red. All right, if I want to plot, we'll do purple here. A slope of 1 and a y-intercept at 0, negative 4. In purple, I've got 0, negative 4. That gets me started, and I have a positive rise over run. So I rise 1, run 1. Oh, we already have an intersection point. Rise 1 and run 1. We would drop 1 and run 1 to continue the line underneath. And indeed, these two lines do intersect, and we would have a point of intersection here at 1 for x, negative 3 for y, and our solution is 1, negative 3 is an ordered pair, showing the intersection of the two lines graph from slope and the y-intercept onto the graph. This is a really pretty point. You can kind of see it when we graph both lines, and then look for that point of intersection, which causes the expressions to become a system and work together. So eventually they intersect and they connect. So now they have a common point at 1, negative 3. All right, another example. If you're asked to solve the system by graphing, you're looking at that intersection point. If you're given something like x minus y equals negative 5, and you're given something like 3x plus y equals a negative 7, remember you want y equals mx plus b form. So you need to work back to that. We're going to subtract x from both sides here. We'll have a negative y equals negative x minus 5. And then we want everything to be positive in the front. That negative y, we want it to be positive. We're literally just going to multiply the whole equation by negative 1. It'll flip every sign in the equation. We'll have a positive y equals a positive x and a positive 5. That's because you're multiplying all of those negatives by negative 1. It's going to make a positive y, a positive x, and a positive 5. Okay, so now we'll pull our slope. Our slope is a 1 over 1 right here, rise over run. Our slope is 1 in the positive. If we plug a 0 in for this x, that just leaves 5. Y equals 5. So 0 for x, 5 for y for the y-intercept. Okay, we've looked at this. All right, so same here. We're going to subtract 3x from both sides. That leaves a positive y. We're in good shape there. Equals negative 3x minus 7. As long as your y is positive, you're in good shape. So now we have our slope is a negative 3 over 1. Remember, you can put any whole number over 1 for that rise over run. And if we put in 0 for x and multiply it, then that y is going to equal a negative 7. So 0 for x, negative 7 for y. Okay, so what we do is we individually plot these. I'm going to do the first equation in the red, with a slope of 1 and a point of 0, 5. So 0, positive 5, and a run of 1, a rise of 1, so rise over run. So we have a positive slope emerging that will continue on. So what am I doing here? I'm doing a rise of 1, a run of 1, a rise of 1, a run of 1, because that's what our slope says in this one. Okay, that's where that comes from. Rise over run equals slope. So be confident and count those out. Alright, in our next one, we have a 0, negative 7. It's a little bigger than my chart, but that's okay. I'm just going to do this one in red. So down here, I am going to plug in a point at my 0, negative 7, but it's just right at my smart keys. Okay, and then we have a slope at negative 3, 1. So we're going to have a negative slope. And it's got to go all the way up to intersect the blue line. So we're going to say, all right, so we're at 7, 6, 5, 4, 1. Okay, let me fix this. I'm just super close to my smart keys. Alright, so we're going to land at a rise of 3, a run of 1, a rise of 1, 2, 3, and a run of 1. So it would look like this: 1, 2, 3, a run of 1. We're going to plot that line. So here's our rise of 3, run of 1. Here's our rise of 3, run of 1. Here's our rise of 3, run of 1. Now we're intersecting. I'm trying to be careful to not put other points on the graph here. So we have an intersecting line that causes a system with these two expressions, and that falls at a negative 3, 2. And that's our solution to the system in an ordered pair format presentation. So we call the solution the intersection of the two lines graphed by slope and y-intercepts onto the graph. Alright, if you solve the system by graphing and you are given something like x plus y equals 3 and 2y equals negative 2x plus 6. You want y equals mx plus b, slope-intercept form. So move your equations to that form so you can isolate your slope and your y-intercept to start graphing. That's your first steps. Okay, there is a chart on page 280. There's a chart. And you need that chart for notes. A copy of it, copy it over, take notes on it, put it on index cards, whatever it takes to refer to it and set it out while you're working and think it through. We're going to get to this chart and how it works with our solution shortly. So, okay, x plus y equals 3. We're moving it into y equals mx plus b form. Subtract x from both sides. That's y equals negative x plus 3. That means our slope is a negative 1, because invisible math right here. And that means our y-intercept is a positive 3, because if we plug 0 in for x, all that's left is 3. So there's the point for the y-intercept, which is the b term in the intercept equation. Okay, so looking at this, 2y equals negative 2x plus 6. Divide by 2 all the way across. Keeps your equation equal across the equal sign. We're going to have y equals a negative x plus 3. Alright, now it's in y equals mx plus b form, and we know that this is now going to be a negative invisible math, 1 over 1, rise over run for your slope, so m equals a negative 1. If we plug in 0 for x, it's just y equals a positive 3. So 0, 3 is the y-intercept. What do you notice about the slopes and the y-intercepts? They're the same. For the two equations. You have the same slope. If you remember, that's going to be parallel lines. So let's graph each equation. We're going to have 0, 3 for our red equation with a slope of negative 1. So a negative rise over run, and it's going to be a negative slope visually, and the line will continue here. You have that. Watch what happens when we graph the blue line at a slope of negative 1 at a y-intercept of 0, 3. So we've got the blue line going here, and we're going to have a negative rise over run of 1. Okay, rise over 1 of 1. So this is the blue graph. It's continuous on the same line. Look at your chart on page 280. When this happens, there's the exact same y-intercept, the exact same slope. These solutions are infinite. You can plug in any x or y value and have a solution for both equations if they are the same. Alright, x plus y equals 3, and x plus y equals 7, and we want y equals mx plus b form. And we're doing the same thing, solve the system by graphing, refer to your chart on page 280 about the solution set. And if we move this to y equals mx plus b form for both equations, we're going to subtract x from both sides here. We're going to have a y equals negative x plus 3. We're going to pull our slope. That's a 1 over 1. So our slope now equals a negative 1. And our y-intercept is the b term, which equals 3, which is a 0, 3 ordered pair, because you're plugging in 0 for x and all that's left and the equation is 3. So that's our first plotted point that starts getting our graph down. Okay, see the pattern? We've been working the same pattern over and over again. Hey, we're going to subtract x from both sides here. We're going to have y equals negative x plus 7. And we're going to consider our slope is a negative 1 over 1. And our y-intercept is a b, and it is 7. Oops, my brain wrote down 3. Okay, so it is 7 for this one, and we plug in 0 for x. Alright, so we have a 0 for x, 7 for y, and we're going to go and graph our first equation, 0, 3 to get started, and then a rise over run of negative 1. So 0, 3, 0 for x, 3 for y, and we're going to have a rise that's negative 1, a run of 1, a rise at negative 1, a run of 1, a rise at negative 1, a run of 1, and we can continue the line above, and we're going to have a negative slope emerge from that equation. Okay, so now we'll graph the green one. We have a positive 0, 7 to get started in green. And it's a little bit up here off my graph. That's okay. So we also have a negative slope, a negative rise of 1, run of 1, a negative rise of 1, run of 1, and that continues to graph. It would graph above too, but we can see the green runs parallel to the red. There's no solution because systems of equations are a system when the line visually intersects on the graph at a certain point, and that's where the two equations work together. There's no solution here. So it's a null set solution, no solution. There's no point of intersection on the graph. Alright, there is a graph example. I believe it's on page 281, example 5, to go through on your own. I would suggest that you not only read it the first time and go through it, but also sketch out all the parts by hand to really understand the input and the output on the x and y. Remember, the x is an independent variable, the y is a dependent variable, and you're looking for the intersection of the information. Look at how to set up the equations and where everything lands from the information on the graph. I hope this helps, and I'll see you soon.